Section: Introduction. In this section, we will discuss the challenges faced by large language models, LLMs, due to their high resource demands, hindering the development of powerful and accessible AI. While modern LLMs have shown impressive performance surpassing humans in some tasks, they are still inefficient and rigid. Most LLMs use dense models, where all parameters are utilized during both training and inference. To address this issue, the mixture of experts, MoE, architecture has emerged as a popular solution, allowing for parameter scaling while keeping computational costs reasonable. Recent advancements in MoE architectures applied to transformers have led to successful attempts at scaling language models to a significant size, resulting in models like DeepSeek MoE, Mixtral 8x7b, Grok 1, and DBRX with remarkable performance. However, these models are not fully open-sourced as their training methods are not shared and may involve proprietary datasets inaccessible to the public. The open-source community has also worked on training MoE models, such as OpenMoE, but their performance is comparable to weak dense models like OpenLLaMA and TinyLLaMA. To address the need for more accessible and cost-effective LLMs, especially MoE models, we introduced JetMoE 8b. This innovative MoE architecture, inspired by module former, extends sparse activation to both attention and feed-forward layers. Unlike previous works that only applied sparse activation to the feed-forward layer, JetMoE-8b utilizes sparse activation in both components to further reduce computational costs while maintaining performance. JetMoE-8b is trained with a limited budget and open-source datasets, outperforming models like Llama2-7b and Llama2-13b chat while significantly reducing inference computation compared to Llama2-7b. The key advantages of JetMoE-8b include its openness, academia-friendly training using public datasets and open-source code, sparse activation in both attention and feed-forward layers, and a comprehensive open-source data mixture for high-quality training. The mixture of experts, MoE, layer in JetMoE consists of modules and a router that selects the top experts based on a probability distribution predicted by the router. By using a sparse mixture of experts, SMOE, approach, JetMoE reduces computation costs during training and inference. Each feed-forward expert in JetMoE is a standard two-layer MLP with specific parameters for input and output projections, enhancing the model's performance. Overall, JetMoE 8b's innovations pave the way for more accessible and efficient LLMs, benefiting the broader AI research community. We have detailed all training parameters and data mixtures in this report to encourage collaboration and further advancements in the field. Section Summary. In this section, we introduce the challenges posed by resource-intensive large language models, LLMs, and the emergence of the mixture of experts, MoE, architecture as a cost-effective solution for scaling language models. We present JetMoE-8b, an innovative MoE architecture that incorporates sparse activation in both attention and feed-forward layers, significantly reducing computational costs while maintaining high performance. JetMoE-8b outperforms existing models like Llama2-7b and Llama2-13b chat, showcasing the potential for more accessible and efficient LLMs in academia research settings. Section: Attention Expert. In this section, we propose the mixture of attention heads, MoA, to enhance SMOEs with attention mechanisms. We modify MoA by allowing multiple heads per expert and incorporating rope relative positioning into the attention calculation. In JetMoE, each attention expert consists of four matrices: W _Q _E, W _K, W _V, W _O _E. The dimensions are defined such that D_at equals H times D_head, where H is the number of attention heads in each expert, and D_head is the dimension of each head. The matrices W _Q _E and W _O _E are specific to each expert, while W _K and W _V are shared among experts to enhance training and inference efficiency. When given an input vector sequence x, we first project it into key vectors k and value vectors v, using the shared key and value projection matrices. Within expert E, we further project x into query vectors q_e, apply standard multi-head attention with rope, and then project the attention output back to the input space. By introducing MoE, we can increase the attention layer's capacity with more experts without increasing the computational load significantly. This prevents the attention layer from becoming a performance bottleneck as we scale up the MLP layers. To ensure balanced training during pre-training, we implement various load balancing techniques in the JetMoE to prevent one module from being overused while others remain underutilized. This involves load balancing losses to regulate the training of the router. In JetMoE training, we utilize frequency-based auxiliary loss and router Z-loss to enhance training stability. The final training loss is a weighted sum of 3 losses, where the weights for load balancing loss and Z-loss are denoted as alpha and beta respectively. We utilize the refined web dataset, which contains 5 trillion tokens refined from Common Crawl using the Macro Data Refinement (MDR) pipeline. Additionally, we use the star coder training data sourced from the Stack version 1.2, encompassing code from GitHub across 86 programming languages. The Dolma corpus is a vast English text collection comprising 3 trillion tokens from various sources, including web pages, code, social media conversations, academic papers, public domain books, and encyclopedic content. The Pile dataset is an 825 GB English text corpus comprising diverse publicly available datasets for training large language models. Furthermore, we leverage various other datasets such as ProofPile2 for mathematical and scientific documents, Open Web Math for English mathematical web text, Stack Math QA for curated mathematical questions and answers, Open Assistant for human-generated conversation corpus, XP3X for multilingual prompts and datasets, and CommitPack-FT for high-quality commit messages from public GitHub repositories. Lastly, we utilize OpenHermes 2.5, a comprehensive compilation of open-source and synthetic datasets for instruction and chat samples following a shared GPT structure. Section Summary. In this section, we introduce the mixture of attention heads, MoE, within the JetMoE framework, which extends SMOs to attention mechanisms by allowing multiple heads per expert and incorporating rope relative positioning. By utilizing MoE, we can efficiently scale up the attention layer with more experts while maintaining computational efficiency, preventing it from becoming a performance bottleneck as we increase the MLP layers. Additionally, we implement load balancing techniques during pre-training to regulate the training of the router in JetMoE, ensuring that the model effectively utilizes all modules and avoids wasting capacity. Section: Ultra Textbooks. In this section, we present a detailed overview of the datasets and infrastructures used in our study. We have gathered a wide range of high-quality synthetic and human-written textbooks from various sources to create the Ultra Textbooks dataset. Additionally, we have curated a subset of the UltraChat dataset, named UltraChat 200K, by filtering out dialogues generated by ChatGPT to ensure grammatical correctness and appropriateness. Moreover, we introduce the template GSM dataset, which contains a vast collection of grade school math problems with solutions in both code and natural language. The Magicoder EVOL 110K and Magicoder OS 75K datasets are generated using the OS Instruct approach, leveraging a large language model, LLM, to create new coding problems. We also present Evil Code Alpaca, an open-source implementation tailored for code instructions. For infrastructures, we utilize Megatron as the training framework and integrate Megablock for support in Mixture of Experts, MoE. We have made modifications to the training framework to accommodate mixture of attention, MoE, and Z-loss. Unlike the common practice, we opt for pipeline parallelism over expert parallelism during training due to its efficiency in sparse MoE models. The hyperparameters for JetMoE 8B are selected based on the 1B transformer language model, with self-attention and MLP layers replaced by MOA and MO. The model is trained with the ADAM-W optimizer, employing the warm-up stable decay (WSD) learning rate schedule. We train JetMoE-8B on a diverse dataset mixture, primarily consisting of English data from web documents, mathematics, and code. Our training process is divided into two phases, with an emphasis on high-quality data during the learning rate decay phase. While our data mixture may not be optimal due to resource constraints, it serves as a solid foundation for training JetMoE-8B and can be refined in future iterations. Section Summary. In this section, we present Ultra Textbooks, a dataset comprising a variety of high-quality synthetic and human-written textbooks sourced from multiple repositories. Additionally, we introduce UltraChat 200K, a subset of dialogues from the UltraChat dataset filtered to enhance grammatical correctness and remove inappropriate dialogues. Furthermore, we describe various datasets like Template GSM, Magicoder, Evil Code Alpaca, and Share GPT, along with the infrastructures and hyperparameters used for training JetMoE-8B, emphasizing the importance of pipeline parallelism in the training data mixture for optimal model performance. Section: Distilled Supervised Fine-Tuning, DSFT. In this section, we present the Distilled Supervised Fine-Tuning, DSFT, process. We train a student language model to respond to user prompts using data generated by a teacher model like GPT-4 or Claude. The key steps are as follows. 1. Data distillation. We generate responses for a set of seed prompts using the teacher model and refine the instructions based on this data. 2. Instruction tuning. The student model is trained by maximizing the likelihood of the responses given the instructions. We approximate the likelihood function by taking the arithmetic mean over a batch of training samples. Next, we introduce Distilled Direct Preference Optimization, DDPO, which further refines the DSFT model by incorporating preferences from an aligned teacher model into the training process. It optimizes a reward function to align the student model's outputs with desired outcomes based on a static preference dataset. The foundation of DDPO lies in KL-constrained optimization, which aims to derive the optimal policy that maximizes expected rewards while minimizing divergence from a baseline policy. The optimization objective focuses on aligning the student model with the teacher model's preferences using instruction response pairs. Offline DPO optimizes language model policies using static preference data, offering stable learning compared to reinforcement learning from human feedback, RLHF. However, it faces challenges with distribution shifts between the dataset and the evolving policy. Online and iterative DPO variants address this issue but come with increased computational complexity. Moving on to alignment details, we use the Alignment Handbook with PyTorch 2 and DeepSpeed 03 to fine-tune the JetMoE-8B base model using DSFT on various datasets. We then further fine-tune the model using DDPO on the Ultra Feedback dataset to create the JetMoE-8B chat model. The entire alignment process takes 60 H100 GPU hours. For evaluation, we measure the performance of JetMoE-8B on tasks from the OpenLLM leaderboard and other domains. We compare JetMoE-8B models to external open-source LLMs and evaluate code generation using Human Eval and MBPP. JetMoE-8B outperforms other models on the OpenLLM leaderboard and achieves high scores in various tasks. Despite some limitations in coding and extraction tasks compared to larger models like GPT 3.5 Turbo, JetMoE-8B Chat demonstrates strong performance across different dimensions, establishing itself as a competitive model in the open-source LLM landscape. Section Summary. In this section, we introduce Distilled Supervised Fine-Tuning, DSFT, a process where a student language model is trained to respond to user prompts using data generated by a teacher model like GPT-4 or Claude. The key steps involve data distillation to refine instructions and instruction tuning to train the student model by maximizing the likelihood of responses given the instructions. Additionally, we discuss distilled direct preference optimization, DDPO, which refines the DSFT model by optimizing a reward function based on preferences from an aligned teacher model, aiming to align the student model's outputs with desired outcomes. Section: Limitation and Future Works. In this section, we acknowledge the limitations and future possibilities of our work. Due to our restricted budget of $100K, we were unable to conduct an ablation study on the model architecture. The selection of hyperparameters and data mixtures was done manually, relying on insights from past studies. Moving forward, it would be valuable to delve deeper into understanding the specific impact of individual components on the overall outcomes.